All right, so now we're going to talk about cardinality. I'm first going to start with infinite sets. So these are sets that go on to infinity. And usually we see these sets with the ellipses at the end. So for instance, an infinite set might be our natural numbers. And they have this ellipse at the very end, the little dot, dot, dot. So we're talking about our infinite sets. And infinite sets can fall into two categories. So the first category is this LF null. It's kind of like a squiggly N with a 0 down here in the subscript. It's actually from the Hebrew alphabet. And then our second set is the continuum. So it's with a little c. Now for a long time in math, we thought all infinite sets were the same size. They were all just infinite. They went to infinity. And then there was a guy called Cantor, Georg Cantor, and he was actually working on fractals, which is one of our other sections right now, one of my favorites, and realized that there were different sizes of infinity. There was infinity, and then there was like this huge infinite infinity. So he realized that we needed to have two ways to describe what are called their cardinality. And cardinality just means how many things are in the set. So there are two ways to figure out infinity, or two ways to count it. This LF null, there are lots and lots and lots of these, so I can't list all of them out, but I can give you some examples. LF null, the natural numbers are our basis for this. All natural numbers, anytime I write out the list of natural numbers, that cardinality of that set is LF null. And this is just set. There's not any work to do with it. This is just something we know about the natural numbers. The same can be said for the whole numbers. The integers. Integers are things like -3, anything that's negative and positive, no decimals. And the rational numbers, which are all the decimals that stop or have some sort of repeating pattern. So like 1/3 has 3 that repeats forever and ever. So anything that can be written as a fraction are our rational numbers. These all have cardinality LF null. We also have any subset of these. So if we just talked about the even natural numbers, that could be another example. So there are lots and lots, there are actually infinitely many lists that can go under LF null. So most of our infinite lists have cardinality LF null. That's just a set rule. There are two special lists that Cantor discovered, and he realized that the irrational numbers do not fit this same LF null. He realized and proved that there are more irrational numbers than natural numbers, which, you stop and think about it, is a little crazy because there are infinitely many natural numbers. They go on forever. But Cantor realized even though that's infinity, he found an infinity that was larger than infinity. We already knew that these infinities were the same. And we know that because we can set up a one-to-one correspondence. In fact, that's something that we and you guys are going to be practicing, is setting up the one-to-one correspondence where you have to find the formulas. We can set up a one-to-one correspondence with the natural numbers and the whole numbers, the natural numbers and integers, etc. if we wanted to. We cannot do that with the irrational numbers. And if we remember way back to our different number sets, the irrational numbers are part of the real numbers. So the real numbers also have this cardinality of continuum. There are only two sets that have cardinality continuum. That's irrational and real. All the other infinite sets in the entire world are going to have the cardinality LF null. So if you don't see one of these two, you know the cardinality is LF null. Now, a couple little minor points about cardinality. There are different ways that we might see the natural numbers written. So we might see the natural numbers written starting at 1 and going to infinity. Or we could see it written in fancy set builder notation. So we may have x. This little line just means such that x is a natural number. And this is just really formal math writing. But all you have to do is go see if they're talking about natural number. The same can be said for these other sets as well as the irrational and reals. So if you see the set builder notation, just look to see what word they've used to describe the set. The whole numbers could be written as the whole number starting at 0 and going forever, or they might be written as x such that x is a whole number. So there are a couple different ways that we can see them written. Sets that are infinite are either going to be written in set builder notation like this with the words, or they're going to have the ellipse at the end of the set. So 1, 2, 3, etc. There are sets that are not infinite. So let me talk about those very quickly. All of these sets we discussed on one of our previous tests, the difference between rational and irrational and whole numbers. We have not talked about a set that might look like this. That set is not infinite. I know it's not infinite because it stops at 10. It does have an ellipse, but it's in the middle. So that means this is just kind of a shorthand, lazy way of saying all the numbers between 1 and 10. We didn't want to have to list them all out, so we just used the ellipse in the middle to save time. So the cardinality of this set, remember the cardinality just means how many things there are in the set. Before we were talking about infinity, this is an infinity, so I can just count up the things in the set, where there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The cardinality of this set is 10. We could also see a set like that. These are the letters. Again, this set is not infinite because there's something at the very end. The ellipse is in the middle, so that just means all the missing pieces. And you need to count the missing pieces. We were just lazy and didn't want to write them out. So these are all the letters in the alphabet. So the cardinality of this set is 26 because there are 26 letters in the alphabet. We just didn't want to write out all 26 symbols, so we used the ellipse to help us in the middle. So when dealing with cardinality, if it's a finite set, if it stops, there's something at the end, then we actually count how many things are in the set, either on our fingers or with something we already know about the letters in the alphabet. For infinite sets, ones with ellipses at the end, we have to decide if it's LF, null, or continuum. The only ones that are continuum are the real numbers and the irrational numbers. Everything else that's infinite is going to have cardinality LF null, which is the little squiggly